Hello there, children. Today, we are going to be working on section 2.3, the remainder and factor theorems. This education experience is brought to you by your foolish teacher of factor theorems. That would be me. So today, we're going to lead into two big theorems, which will help guide us the rest of the chapter. Alright, so remember, the reason we're doing all this is because we have these real zeros of polynomial functions from the last section. Remember, all four of these are equivalent. That means if x equals a is a real zero, that's the zero of the polynomial, it's a solution of the equation f of x equals 0, x minus a is a factor of that polynomial, and a comma 0 is the intercept of that graph. So that's the reason we're doing all this, because if I can find some zeros, then I can apply all of these special properties to help me work with the problem. Now, in order to do any of this, we must work with polynomial division. And polynomial division simply let f of x and d of x be polynomials. Now, big thing is you have to be dividing by a polynomial that has a smaller degree than f of x, and it can't be 0. Basically says when you divide two polynomials, you're going to get a remainder, right here, and a quotient. So you're going to get some stuff, and then a remainder. Your remainder always goes over the thing you divide by. So that's very important for us. So when we divide polynomials, we are going to get a quotient, and we're going to get a remainder. Now, how we deal with that is pretty important. Now, before we really get rolling here, we have to remember how to divide. The division we will most be using in this class, synthetic division. And here is the synthetic division algorithm. Now, you should have seen this in Algebra 2, but if you didn't, essentially you have this. You take the thing you are dividing into, you take all its coefficients and you put it right here in descending order. And if you are missing one, you need to put a placeholder. Like, well, if there was no x squared, you need to put a 0 there. Placeholders are a must. If you do not have placeholders, you will get the problem incorrect. Now, you take the thing you are dividing by, that binomial there, a binomial with a coefficient of 1, exponent 1. Whatever is right here, the opposite sign goes in your box there. And here's how it works. The first number you drop down or add it to 0. Then you multiply by the number in the box, drag it up, add it, multiply it, drag it up, add it, multiply, drag it up, add it. As is written here, that you rinse and repeat that. Now, what happens is, this last term is your remainder, and these are your coefficients of your quotient. So it goes remainder, constant, x, x squared, so on and so forth. That is how synthetic division works, in case you forget. There is a more wordy verbal definition right here, if you so choose to read that. Now, what are we going to use this for? So we have synthetic division and remainders. If r is the remainder, r means remainder, obtained after synthetic division of f(x) by some x minus c, the following statements are true. R is the value of f of c. What that means is, if you want to know if something's a remainder, and you have a c value here that you would use in synthetic division, whatever number you put in the box for synthetic division, you could throw into your function and get the remainder. Now, if r equals 0, then x minus c is a factor. And if it's a factor, folks, it goes back to the first slide we did today, or the second slide technically, where it was all those things from our theorem from last section. So that's really important to us if the remainder is 0. But, just going over a few things here quickly, we have the following. The remainder theorem simply states this. If a polynomial f of x is divided by some x minus k, the remainder is r equals f of k. Or, last problem, if you wanted to write it as such, to keep consistent, that is that x minus c here would state that r equals f of c. So what that means, whatever number you would put in the box for synthetic division, you could put into your function, and that gives you a remainder. Now, where is this helpful? It is helpful to build upon something called the factor theorem. And what in the world is the factor theorem? The factor theorem simply states a polynomial f of x has a factor if I put that in and get no remainder. So how is this going to be helpful? Which should make sense. If I get no remainder, something's a factor. Let's simply divide 7 into a number. Oh, I don't know. What number would be a great number to divide into? 77. That's 11 times. With no remainder. No remainder. Obviously, 7 is a factor of 77. That seems pretty obvious. This is where this factor theorem comes from. If I get no remainder, something's a factor. But how is this going to be helpful to us? Observe. Alright, so use the factor theorem to state if the following binomials are factors of this function there. So I have this. I say x minus 2 is a factor of that. Now, you could go ahead and attempt to factor this. It would be a pain. And then you can look and say, hey, are these two things factors of those? Well, that's possible. Or you could do division, namely synthetic division. So let's first tackle this one here. We're going to first tackle part A. Now, if this is the thing I claim to be a factor, the number that would go in my synthetic division box is 2, the opposite of it. Then I take all my coefficients here. 3, negative 1, negative 22, 24. And I go ahead and I do synthetic division on those. I can have these in order. 3, 2, 1, 0. Those are my exponents, so we're good. Drop the first number down. Multiply. Add. Multiply. Add. Multiply. Add. I get a remainder of 0. I get a remainder of 0, so the first answer is yes. Yes, you x minus 2. Yes, you are a factor. Yay! Woohoo! Alright, now. And we could go forth from this, building the polynomial. That's x minus 2. And then I have this material left. There's my constant of negative 12. There's my coefficient of x. There's my coefficient of x squared. Now, let's say I tried the next one first. Let's say I tried x plus 5. Let's say I tried x plus 5 first. I'll do it in red here. So let's say I tried x plus 5. The number that goes in my box is a negative 5. Negative 3, negative 1, negative 22, 24. Drop the first number down. Multiply. Add them. Multiply them. We're going to add them. Now, you can kind of see where this is going. 58 times a negative 5. Well, that is negative 290. And negative 290 plus a 24, and plus only the 24, is negative 266. Alright, is the factor? No. Why isn't it a factor? Why the heck not? Look over here. I've got a remainder. A remainder that isn't 0. When the remainder isn't 0, it's not a factor. Womp, womp, womp. Sad face. Single tear. if you listen real closely, you can hear the pity party they're throwing for x plus 5 because it's not a factor. Bummer. I was really hoping, but it's not. So that's what we're going to do right now. They're going to give us things like, hey, is this a factor? And we go, well, we'll check. Using our factor theorem and remainder theorem. You are now ready to tackle all assignments for section 2.3. You're going to crush them like Rocky crushes communism in Rocky 4, which is Ivan Drago. You will break it. Go henceforth and do. Woo!